We talked briefly about reminding us that we have intensive and extensive properties. And thermal energy is associated with the motion of particles. And when we look at the average kinetic energy of a whole sample of particles, that average kinetic energy is proportional to the temperature. Temperature is our measure of thermal energy or heat. So temperature is an intensive property. It does not depend on the sample size. Whereas thermal energy, the total amount of energy due to that motion, depends on the total number of particles. So that is an extensive property, and we went through these examples. So let's talk about heat transfer. Heat always flows from high temperature to low temperature. So we have to be careful because there's some tricky parts about the sign of energy of heat and the flow and how it's defined. So we're going to take some time to really refine those definitions so that when we talk about it, we understand clearly whether it's going into the system or out of the system and what is the system. Okay, so these are really important to sort out with the terminology so that our understanding can be based on fundamental principles, and then you can reconstruct it instead of just getting confused by remembering is it positive or negative. Heat always flows from hot to cold. So if you burn your hand on a frying pan, what lost the heat? The pan loses the heat. Your hand got too hot and burned. It absorbed the heat. What about eating ice cream? I know it seems so easy right now, but just wait, it gets confusing. Right? So when you eat ice cream, your tongue is giving up the heat. So your tongue loses the heat. And the ice cream gains the heat and it melts. So when we talk about heat transfer from one object to another, we often define the heat that's lost by one thing equals the opposite of the heat that's gained by the other, right? The heat lost equals the heat gained, but because it's flowing from one to the other, one lost it and it went down and one gained it that went up. So I like to formulate this in a more general way, and that is by adding the heat among the different objects together and summing them to zero. So this is essentially for two things, it's essentially the same as that first equation. So if we have two things, then the heat lost by one object plus the heat gained by another object equals zero, representing no loss to the environment. We're just going to assume it all went from one thing to the other, and we didn't lose it to the environment because it was an insulated system. For the heat terms, the Q, that have a temperature change, the amount of energy, the amount of heat depends on the difference in temperature. And that goes all the way back to our first definition of energy as to raise the temperature of a substance, the calorie, to raise 1 gram of water by 1 degree C. So there was that degree C part, that temperature change. So the heat is proportional to the temperature change. It depends on how much, right? Because it's an extensive property. And it depends on C, which is the specific heat or the heat capacity. That's a value we look up. Now the nice thing about writing this heat transfer equation is because if you have three things, then you can just add a Q in there. Maybe there's Q of one thing, and then there's the water, and then there's a metal, right? So it's easy to generalize, but we're just going to work with two things for a little bit. Let's set up this experiment. All right, we're going to have a beaker with water in it. Sorry, it's not a great drawing. And it is on a hot plate. All right, so maybe I'll put a little fire on there. But really, we're going to use a hot plate. It's not a fire. Right, so this is at 100 degrees C because it's boiling. And inside there is a little piece of gold. Now we're going to take that gold out and we're going to put it into another beaker. And this is at room temperature. So let's say that's about 25 degrees C. Now we're going to take that gold out and we're going to put this hot gold, put it into the water. So when we do that, what's going to happen to the temperature of the water? in beaker number 2. This one is number 2. Yeah, we put this hot metal in the room temperature water. It's going to transfer its heat to the water. So the water is going to get warmer. So the temperature will go up from the water. So what lost heat? The gold, and the water gains the heat. All right. Why do surfaces like a metal railing or a stone counter feel cold? They're sitting in the room with you. Are they not at the same temperature? Let's see. These are at room temperature, but they feel cold. But if you touch paper, it doesn't feel as cold, or wood doesn't feel as cold. But these things, the metal railing feels very cold. So one issue is that the metal will change temperature very easily. It has a low capacity, a low specific heat. It just flows that heat right out of you. Is your body at room temperature? No, we're warmer. Yeah. And then that heat flows easily into the metal or the marble. All right, so we're going to define some words for whether heat goes into the system or out of a system.
So, Professor, does that mean that we are losing heat when we touch that?
Yeah, that's why it feels cold. Exactly. Okay, so endo means in, exo means out. So if a change requires heat to go in to make it happen, then it's endothermic, and that can be expressed as a reactant. Here we're showing heat is required to take that liquid water and turn it into the gas. This is a physical change. It's true of chemical changes as well. A chemical change can require energy, and then that energy will be a reactant. So energy goes into the reaction. I'm writing that physical change with a chemical equation. So it's still a physical change, but we can see it in a reaction form. So energy is the reactant side. Into the reaction, that means it's a reactant. Exo means it's out. Now, in these examples, we're just flipping that process. So what I'm saying is that when that gas water condenses back to the liquid, it's going to release heat. The heat comes out. That means it's a product, and that is exothermic. And that could be for a physical change or for a chemical change. And it's exactly the same amount, right? It takes the same amount of energy to vaporize the water, certain amount, one sample of water, and that same energy will be released when it condenses back down to the liquid. We can think about whether the products and the reactants have where their energy is relative to each other, right? So on our energy axis, when we had a solid, liquid, gas, if we spread that out in time, right, if we start at, I don't have that much room. If we start out in this is the gas, and here's the liquid, and so if I spread it out, right, basically there's this difference, right? So I started up here, and I went down to here. So all of that heat must have been released. So we'll look at those energy diagrams again. But anytime we go up on this axis, we have to add heat to the system. So that will be endo. And anytime we go down on that axis, heat will be released. So you can think of before and after. Okay, so what does that mean? For freezing, which one of those arrows is freezing? That's making a solid, right? That's a liquid to a solid. This one would be exothermic. Heat will come out of the system when it's exothermic, and that Q term is going to have a negative value, and that's where it can be a little bit confusing. Exothermic is negative because heat comes out of the reaction, and we're going to address that in just a second. Okay, let's look at vaporizing. Which arrow is that? That's going to go from liquid to gas. So endo or exothermic? It's endo because you have your energy and you want to go up, you have to put energy in to go up. So this one is endothermic. And that Q is going to be positive because energy has to go in. The system gains the energy. We're always looking at the system, always the system perspective. All right, sublimation. Do you remember what sublimation is? Solid to gas. And so that one is endo, and Q is positive. All right, what's melting? That's going to require energy, endo, and our Q will be a positive value, energy N. And then deposition is the opposite of sublimation. Yeah, exothermic, which means Q is going to be a negative value. Okay, so that's physical changes. Now, these signs get confusing because we always are going to look from the system perspective, and everything else in the world is going to be the surroundings. Where is our thermometer located? Is that the system or is that the surroundings? It's always part of the surroundings. We're not going to do chemistry to find out about the thermometer. The thermometer is a measurement device. So when a reaction or a change is exothermic, the system gives heat out, right? So the system loses heat. What happens to the thermometer? What happens to the temperature? The temperature increases in the surroundings, right? And if this is confusing, you can always think back. Why do we build fires? Why do we have a stove that heats things? We cook with them, right? We burn wood to get heat out to warm our homes or our food. So heat released means that the surroundings get hotter. If the surroundings get colder, then the system is drawing heat out of the surroundings. And so the system is going to gain that energy, just like moving up on the diagram. So I'm going to add that lingo in here. The system and the surroundings have an opposite relationship, right? If the system gains heat, the surroundings lose heat. So this gets more difficult when we're looking at a reaction, a chemical reaction. Everything's easy when we're talking about ice cream, right? But then we start looking at a chemical reaction and suddenly it's confusing because we have to visualize sitting on the atoms. The atoms are going to rearrange. We have to imagine being on the atoms. That is the system. So here, in this example, the system is the salt. And the solid here, that's part of the system. But then what is the aqueous? This water is in the surroundings. So that can be confusing because especially down below here, we have water that's part of the system, and then we also have water that's in the surroundings. So we have to be really aware that the system is the rearrangement of the atoms that we're looking at. In the lab, oh, but we did the gizmo. You took a powder, I don't think we had ammonium chloride, but you had KCl, and you put it into the solution and the temperature went down, right? If the test tube feels colder as it dissolves, is heat a reactant or a product? The system took that heat out and we gave the heat and felt cold. So heat is a reactant, and this process is then endothermic. Okay, in another example, we would have done this. If you add an acid and a base, and we used HCl, hydrochloric acid, and sodium hydroxide in our lab. And remember, those were 2 molar. It was pretty concentrated, right? So there's that safety question in the pre-lab. Okay, so when you do your post-lab, you know where to look for that. It's in the lab manual pages. So I did want to include some of that safety. And then it forms salt, which is totally inert, and water. And when it happens, the test tube gets warm. So is heat a reactant or a product? I'm going to write it as a product, and then that is exothermic, because when we felt it warmer, heat was released by the system. All right. Now we have this little segment on energy units. So here's the calorie, where this is the amount of energy to raise the temperature of 1 gram of water by 1 degree C, and 1 gram is 1 cubic centimeter, it's a small amount, and this is 1 calorie, or 4.184 joules. But then we look at the label on our food and they have calories with a capital C. That is kilocalories. So our nutritional calories are 1,000 times the scientific unit of calories. So that's like 1,000 milliliters of water to raise it by 1 degree. It's a lot of energy. So when we talk about food values, typically we're going to look per gram of food. And if we're talking about airplane fuel, food is burned, or we might have jet fuel, the mass is really important because they're lifting it up into the air. So they have to figure out a way to have enough fuel without increasing making the plane so heavy that it burns even more, right? They have to calculate the weight of that fuel. So fuel values are always per gram of the food or the fuel. So it's just a different units. Here's an example. This is breaking down sugars, and it produces energy, right? So that's why we eat, get that energy out. And the lab takes us through calculations of this type, but we're going to skip that, so I'm not going to spend a whole lot of time worrying about that. Oh yes, and we talked about light energy. We talked about using light as a flashlight to determine the layout of the atom. So this is in the same chapter because it's energy, but this really gave us the energy differences in the Bohr model, in those energy levels. So we covered this already, but we're reviewing. Which is higher in energy, red or blue light? So we have to remember, do you remember our spectrum? And in the middle we had our visible. So maybe we had red, and on this side, and it went to orange, yellow, green, blue, violet. So which side is high energy and which side is low energy? So this side is low. The next one is infrared, which is just heat, radiant heat. This side is high energy. This is where we get to the UV spectrum that can burn your skin. It can cause changes. So that's how I always remember. On the purple side, it's the UV side. So this would have higher energy, is the shorter wavelength. One way that I can visualize that too is I think we talked a little bit about if you dropped a stone into a still pond and it goes in and it causes waves, and those waves expand out in a ring, and maybe they hit the side of the fountain. And so as each wave hits the side, there's some energy put into the wall. If you think of it as a ball at the top of each wave, the one that hits the more often is going to give more energy. So I think these are some good ways to visualize, visually, this relationship between wavelength and energy. And then also remembering, on the red side, it's like the French fry lights. And on the purple side, it's like the sunburn side. And that was how we knew those energy levels in the atom. So if we have a continuous spectrum like this rainbow, that would be from like an incandescent light bulb. For example, the one I have in here is an incandescent bulb. If we take that light bulb and we put it in one direction and then we split it out in a prism, so all the wavelengths curve a different amount, then we can detect that full spectrum rainbow. But when we have, instead of an incandescent bulb, that's putting electricity across the filament until it gets so bright, so hot that it glows. If we put hydrogen gas inside, there's no filament. It's just electricity going across the closed gas. We only get particular energies out. This is like the fingerprint of that element. So just from this spectrum, from that alone, the distance from the nucleus and the energy of electrons in those different orbitals was determined. It's quite amazing. All right, so this tells us that only certain energies were allowed, right? And so that's the basis of quantization. There's not a continuous amount of energy that can come in and out, only certain quantized values. So here's what we say for the Bohr model. There's only certain energies allowed, and they are quantized by n, the principal quantum level. And that corresponds to our periodic table. Here's our n value, 1, 2, 3, 4, 5. It's right there on the periodic table. Now, if we have a ground state, that's the lowest energy. If we have an excited state, some energy came in and popped it up, and so there's an empty level where it can come back down. And when it comes back down, it gives off some light. That's what these lines are, right? It comes back down and just gives one energy. And so from that, we can construct what's the distance there. Now, the Bohr model only works for one electron at a time, which is a big limitation. So in the early 20th century, the first 25 years or so, the wave mechanical model was applied to electrons in the atom, because those electrons can interact with each other through wave properties. And so we develop our probabilistic model. So we go from saying that this is particles in orbits. This is where are we likely to find the electron. So this is probabilistic. So where does the electron spend time? Now usually it's pretty close to the nucleus, and it gets less likely, but then we just decide, right? We say, okay, we are 90% sure it's inside this boundary. And that's what we're going to call our S orbital. It's spherical. S comes from spherical. So we talk about this like as the electron cloud, where we're likely to find that electron. And so we know from the n value, as we were adding protons in the nucleus and electrons in the outer orbits, that n equals 1 is smaller than n equals 2. And n equals 2 is smaller than n equals 3. So by the time we have something that is, if we have something in n equals 3, that could be like sulfur, for example, is in the third row. Inside there, it's got a 1s and a 2s, and its outermost electrons are in the 3s. P-shaped orbitals have this shape, this dumbbell shape, and they have more directionality. Spherical orbitals are in the same, s orbitals are the same in all directions, and the P-shaped orbitals correspond to this section of the periodic table. And they have three equivalent orbitals that have that dumbbell shape. And one points in X, one points in Y, and one points in Z. So they're 90 degrees from each other. So we know that S is spherical. For S orbitals, there's just one of them in its subshell, and it can hold up to 2 electrons. We'll often represent it like that. For a p orbital or a p subshell, these have dumbbell shapes, and there are 3 equivalent orbitals in the x, y, z directions. Because there's 3 orbitals, they can hold, that set can hold up to 6 electrons. It's handy if you have your periodic table to have it out so you can look at it and understand how we map this onto the periodic table. First, I want to define valence electrons. Valence electrons in the outermost shell. So literally, you can look at the periodic table, write your numbers down the side. This is the highest n value. That outermost shell, that's where all the chemistry happens. So if we look at a chlorine, you find that on your periodic table. Chlorine is number 17. So it has a total of 17 electrons. How many are in the outermost shell? Maybe I'll just draw this. All right, and then here is chlorine. So 1, 2, 3. So there's chlorine. In that outermost shell, right? These guys and these guys, I have 7 electrons in the valence shell. So 7 electrons in N equals 3 shell. All the rest are in the core. So if you go back to the previous noble gas, right, if you go back to here, then that will give you, there must be 10 electrons in the core. 10 plus 7 is 17, so you can figure it out by looking at the total number. All right, so we can map our knowledge right onto the periodic table pretty well. So I'm going to start by just adding this in. And now when I ask you to take an exam, I want you to start with a fresh one, this one by itself blank. If you have one printed out fresh, then you can use that on the exam and then you can make your markings. But I don't want anybody to start with their periodic table that has all their notes on it. So that would be a separate table, right? So I would usually say, okay, I'm going to add my N values here. There's my N equals 1. There's my N equals 2. There's my N equals 3. There's my N equals 4. And so I'm looking at this guy right here. Okay, so the valence shell is going to be N equals 3. So for chlorine, so I'm going to grab that. That's my valence shell right there. I know that I have a total of 17 electrons in chlorine, and I can just count the boxes. I can just count 1, 2, 3, 4, 5, 6, 7 electrons in the valence shell. And that gets me all the way back to the previous noble gas. We know that those noble gases are especially stable. So reactions don't happen in the core. They all happen in the valence shell. So it's really important to understand the difference between the valence electrons and the core. So all of these other ones are core electrons, right? Those are the core electrons, and they're not available for reactions. So 10 core electrons. And you can kind of see that looking at the periodic table with that number. The number of valence electrons is really important. It matches the group numbers in the older numbering. So let me just take a look at adding those in, right? So here's group 1, here's group 2, that's not a 2. Here's group 3, 4, 5, 6, 7, and then 8. Now the noble gases don't really react much, so we're really going to be concerned more with up through 7. That means that the orbitals in the N equals 3 are larger. They're N equals 3 sized. And it also means that there are 3 different regions of the periodic table that have that size. Okay. And it also tells me the energy. So the energy is proportional to the N value. So higher N means bigger with more energy. So N equals 3 says it's of N equals 3 size. And that's a great question because we have these subshells. I'm going to show those really quickly too. This is the 3s subshell. 3s subshell. Right there. In that 3s subshell, we can have up to 2 electrons. So do you remember that I had said every time we add a proton in the nucleus, it makes it a new element? But we also add an electron in the outer shell. So this box represents kind of the unique character of that element. So we have a 3s subshell, and let me just pop a couple more in there. Let's take a look at the P. This is the 3p subshell right there. So that means that all of those elements, their outermost electrons have a size of about 3, an energy of 3, and they have that dumbbell shape because they're in the p subshell. So we know the shape, we know that there's 3 equivalent orbitals. Each orbital holds up to 2 electrons. So you get 1, 2, 3, 4, 5, 6, up to 6 electrons in the 3 orbitals. So you know the size and energy, you know how many there are, and you know the shape just from this 3p designation. Have a good day. I'll see you later.